I'm Joseph Russell, and this is a quick explainer of my paper, Human Dead Reckoning Using a Particle Filter and Map Constraints, by me and Jeroen H.M. Bergman. So there are lots of fields where it's useful to be able to know where a person is. For example, if you're physically disabled and you want an assistive robotic device to be able to help you in the home, it ideally needs to be able to tell what it is that you want it to do. And to know that, it's really helpful for it to know where you currently are. Now you can do this on a large scale using GPS, but on a small scale, like in your house, that's nowhere near accurate enough. Now you can do this using extra hardware like Bluetooth beacons or cameras, but wouldn't it be nice if all you needed was your smartwatch or your phone? Devices like these contain inertial measurement units, or IMUs, which record acceleration, angular velocity, and orientation. To get position from acceleration, you have to integrate once to get velocity, and then again to get position. This is called dead reckoning. The trouble is, IMUs aren't perfectly accurate, and any small error in acceleration, orientation, or starting position can grow rapidly over time. So if you integrate the raw IMU data, the estimated position very quickly drifts away from reality. In this paper, we investigated whether a particle filter could be used to reduce that drift, using only the IMU data, the physical constraints of the human body, and a known map of the space. Essentially, we take a starting point and then simulate thousands of possible positions a person could move into, based on the IMU data and how inaccurate we think it might be. We then discard the options that aren't possible, either because they're faster than a human can move, or because they take our person outside the map. To show you how this works, let's take a simplified example. Assume we have one particle in the bottom right corner of this rectangular map. It's about to move, but we don't know in which direction, up, down, left or right. So we simulate all four, apply the movement, and look! Only one remains within the map boundary. So that's probably where the person is. Of course, in our study there are actually 100,000 particles, and there are way more than just four directions a person could move, but hopefully you get the general idea. The question we're examining in this paper is, what kind of map should you use? Intuitively, you might simply start with a map of all possible places a person can be. However, this introduces an interesting effect if the path you're walking along is close to the map's edge. Take a look at this particle cloud. Every red dot is a possible position a person could be in, and their true position is somewhere along the blue line, the true path. A good estimate for where the person is from the particle cloud is to take the mean, so let's do that. All good, it's on the line. But look what happens if this path is near the edge of the map. Some of the particles now lie outside the map, so we know they're impossible. So they should be discarded, right? But if you do that, you have the effect of skewing the mean away from the boundary. So applying this map actually made our estimate less accurate, and this is an effect that gets worse and worse the longer you run. So our proposal was, what if you artificially inflate the map by a certain distance? So even though we know the person remained within the map, our particle filter works with the inflated version. So now all our particles remain within the map, and our mean returns to the true path. Obviously this is a simplification, but our hypothesis was that the gist should hold true, so we did this in real life. I walked around our running track at SDU holding an IMU, we applied this methodology, varying the size of the map, and here are our results. So you can see that for our experiment we got the best results by inflating our map to a distance of 8 meters from the true path. More or less than that caused error to increase, and this was a lot better than just using GPS. So that's the key takeaway. If you're trying to do dead reckoning, you don't necessarily get the best performance by using an accurate map of your space. You might get better results by using a bigger one. The full paper is linked in the description down below, and obviously we go into a lot more detail there. If you prefer to listen, I've also recorded an audio version, which I've linked for you too. If you have any questions, feel free to leave a comment down below, and if you'd like to hear more about our research at the Biomedical Engineering Centre, then your best bet is to like and subscribe. Thanks so much for watching.